Just a minute, guys. When I'm about to take this class, I'm having a hiccup again. So just I have to fetch water. Just wait for a few minutes. I'll return in about 5 minutes. I have to fetch water and drink some water. Anyways, I'm having this problem. um, okay, so I think we can start our class. You can enter your attendance in the chat box. All right. So today we have talked about a curvilinear coordinate system, and here we have discussed this 3D Cartesian system with our XYZ coordinate lines and the coordinate surfaces given by x equal to C1, y equal to C2 surface, z equal to C3 surface. So all these coordinate surfaces are perfectly planar surface. Okay. So for every point on this plane, YZ plane, x value is fixed. So that's what the surface equation is. And similar to that, instead of our XYZ system, let's say we consider another coordinate system, U1, U2, U3 coordinate system in place of XYZ. And uh, the equation of the surface, coordinate surface, considering what we have discussed in the case of this Cartesian system, as x equal to c1 as the coordinate surface, we can define three coordinate surface given by u1 equal to c1, u2 equal to c2, u3 equal to c3. If at least one of these coordinate surface is a curved surface, then the coordinate system is called curvilinear coordinate system. And if the coordinate surfaces intersect at 90 degree, then it's the orthogonal coordinate coordinate system. That's what we discussed, right? And we have discussed this tangential unit vectors and these perpendicular unit vectors. Now, we can define what is called an arc length. In a 3D Cartesian system, if you draw a 3D Cartesian system like this, x, y, z, the position of any point can be given by position vector, which is your r vector. Your r vector is given by x, I, y, j plus z, k. Now, arc length means change in this position vector. So let's say the change in position vector, if you move to another point here, the position vector, if you move to another point here, this new vector, you can denote it as r vector plus dr vector. So this dr vector, this is called a small change in the position vector dr. This is called an arc length. So dr in this case will be dr vector will be dxi plus dyj plus dzk. Okay, which you can also obtain it. You know that position vector here in this case is a function of x, y, z. So position vector r vector is xi plus yj plus zk. So you can see that r is a function of x, y, and z. You can consider any change in r, dr as like we discussed before in the case of scalar function, there were derivative of r with respect to one of the coordinate variables into dx plus dr vector upon dy into dy plus dr vector upon dz into dz. So if you take this dr upon dx, you know that this is r vector. So del r upon del x will be del upon del x xi plus yj plus zk. So this will be, if you differentiate it, del x upon del x is 1, del y upon del x is 0, del z upon del x is 0. So you will get I cap here. Okay, and similarly del r upon del y, you will get it as j cap. Del r upon del z, you will get it as k cap. So therefore, from this relation, your dr vector in this case will be I dx j dy plus k dz. All right. So that's how we get this arc length dx here, dr here in Cartesian system. In this orthogonal curvilinear coordinate system also, you can express your position vector as a function of the three coordinate variables u1, u2, and u3. So if this position vector is a function of three coordinate variables u1, u2, u3, any change in r, dr, change in position vector dr, called the arc length here, can be expressed as different this del r upon del u1 du1 plus del r upon del u2 du2 plus del r upon del u3 du3. And del r upon del u1 here, over here, we already got it, right? Del r upon del u1 is equal to h1 into e1 cap. E1 is a tangential unit vector. Del r upon del u2 is h2 into e2 cap. E2 is the tangential unit vector. And similarly, del r upon del u3 as h3 into e3 cap. This we have discussed. So if you just put that h1 into e1, h2 into e2, h3 into e3, so this is what you get as the arc length in the case of this orthogonal curvilinear coordinate system. So the volume element dv, the volume element also you can take it as the triple product for this vector, and this vector. If you take a triple product, magnitude of that, and this gives you the volume element in this curvilinear coordinate system, orthogonal curvilinear coordinate system. So I hope you understand how we write this. Once we have a certain quantity which is a function of multiple variables, then you can express any change in that quantity as this, like we have done in the case of, what is that? I don't know how far I have to go. Just a minute. I have discussed this. So where is that? Yeah. Hmm. Yeah, over here, yeah, we have discussed this. See, if we write phi as a function of phi, if we know that phi is a function of x, y, and z, any change in phi using uh law theorem of partial derivatives, any change in phi can be expressed as rate of change of phi with respect to x multiplied by change in x, rate of change of phi with respect to y multiplied by change in y. Like this we can express, and from here we can write it like this. You remember that. So this here in this case, this quantity you can write it as a dot product between this and this. So you can write d phi as grad phi dot dr. So this is what we have discussed in the Cartesian system. Okay. The phi, any change in phi can be written as grad phi dot dr here. So that is what we already know. Now, let us get back to what we are discussing. All right. Okay. Now let us see how you are going to write a gradient uh, of a scalar function in orthogonal curvilinear coordinate system. So in orthogonal curvilinear coordinate system, instead of your x, y, z Cartesian system, you are now having u1, u2, u3 as the coordinate lines or the coordinate axis. And any scalar function in such coordinate system can be expressed as a function of this, because in the 3D Cartesian system, any scalar function in such 3D Cartesian system can be expressed as a function of those 3D coordinate variables x, y, and z. Similar to that, in this orthogonal curvilinear system also, phi can be expressed as a function of the coordinate variables u1, u2, and u3. So like I discussed, the position vector in the case of Cartesian system, it's xi plus yj plus zk. So the position vector, as we know it, it's a function of x, y, and z in this 3D Cartesian system. Similar to that, we can also write position vector in a u1, u2, u3 coordinate system can be expressed as a function of the coordinate variables u1, u2, and u3. And therefore, using this theorem on partial derivatives, any infinitesimal change in phi, any infinitesimal change in the position vector r can be written like this. Okay, so d phi can be written like I have just shown you in the case of Cartesian system. D phi was written as rate of change of phi with respect to x variables multiplied with change in x. So del phi upon del y, this measures how quickly this phi changes with y multiplied with dy, and similarly del phi upon del z, which measures how quickly phi changes with z multiplied with any step size, any change, any infinitesimal change along z. So similar to that, you can just follow the analogy here. In the case of 3D Cartesian system, you can write the change in phi in terms of u1, u2, u3 coordinate axis coordinate variables as this, and any change in dr can also be written like this, right? So when we discuss the tangential unit vectors, and we have defined the scale factors h1, h2, and h3. So this is what we have, del r upon del u1 as h1 into e1, and this as h2 into e2. So if we denote this as equation 1, equation 3, and here over here you just substitute. So your dr, you can arc length, you can write it as this equation 3. All right. Now, similar to the gradient in 3D coordinate Cartesian system, you know that gradient in 3D Cartesian system is expressed like this: del phi upon del x I cap, del phi upon del y j cap. I, j, and k are the unit vectors, and these are certain functions. After differentiating, it will result in a certain functions, right? So the gradient in this u1, u2, u3 coordinate system, orthogonal coordinate system, curvilinear coordinate system, can also be expressed as something like unit vector. Instead of unit vector, we now have e1 cap. Instead of j cap, we now have e2 cap. Instead of k cap, we now have e3 cap, unit tangential unit vectors, right? And we don't know the form of this, so we will simply write it as f1, f2, and f3, because in this 3D Cartesian system, the coefficient of I cap is del phi upon del x, the j cap coefficient is del phi upon del y. But you know what? Orthogonal coordinate system having coordinate variables u1, u2, we are yet to find what will be the coefficient of e1 cap, coefficient of e2 cap, and coefficient of e3 cap. But we know that the unit vectors, in place of I, we have e1; in place of j, we have e2; in place of k, we have e3, right? So these are some functions that we need to determine. And again, like if you remember, in the 3D Cartesian system, we have written that any change in phi is a dot product with grad phi and dr. This I think I have just shown you also a few minutes ago. In 3D Cartesian system, we can express d phi as grad phi dot dr. Dot here is the dot product. Okay, so if you take grad phi from this expression, you write it here, and your dr, you can take it from equation number 3 here. Your dr vector, you take it from equation number 3. This is what you have as your dr arc length. Now you take a dot product, e1 dot e1, it's a 1. They are unit vectors, right? So if you take a dot product between two identical unit vectors, this will be, sorry, e1 dot e1 will be magnitude of e1, magnitude of e1, and cosine of angle between them. Same vector means cos 0. So e1 into e1 is 1, 1. Cos 0 is 1. So this will result in 1. But if it is a orthogonal curvilinear system, how we define orthogonal curvilinear system? If you remember, we define orthogonal curvilinear system as a curvilinear coordinate system in which the coordinate lines intersect at 90° and the coordinate surfaces intersect at 90°. So if the coordinate lines here, u1 coordinate lines and u2 coordinate lines, u3 coordinate lines, if they intersect at 90° here, as in the case of this here, u1 coordinate line, u2 coordinate line, u3 coordinate line, they intersect at 90°. If they intersect at 90°, the tangential unit vectors e1 cap, e2 cap, e3 cap, they are also at 90°. Okay, e1, e2, e3 cap, they are mutually perpendicular. And similarly, capital letter e1, capital letter e2, capital letter e3, they are orthogonal, right? So in such case, your e1 dot e2 is 0, e1 dot e3 will be 0 if the coordinate surfaces intersect and the coordinate lines intersect at 90°. The tangential unit vectors are also orthogonal to each other in this orthogonal curvilinear coordinate system. Okay, so taking a dot product, e1 dot e1 as 1, e1 dot e2 as 0, e1 dot e3 as 0, and similarly you can find that e2 dot e2 is 1, and rest of the dot product with this and this will be 0. So when you do that, your d phi, you will get this. Okay, your d phi, any change in phi, you will get this expression as in this equation number 4. Now you compare this d phi, change in phi, as given by this equation number 4, and change in phi as given by equation number 1. If you compare these two, the coefficient of du1 here is del phi upon del u1. The coefficient of du1 here is f1 into h1. So by comparison, you can see that uh, f1 h1 is equal to del phi upon del u1, right? So from here you can write your f1 as 1 upon h1 into this del phi upon del u1, and your f2 also you can obtain it as this and this, right? So if you remember, this was what we have assumed in 3D Cartesian system. Grad phi should have the form f1 e1 cap, f2 e2 cap, f3 e3 cap. This is what we have assumed. So you just substitute f1 here, f2 here, and f3 here. This is what you're going to get. Okay. So I hope you understand this. So you just substitute f1, f2, and f3 as we obtained by comparing this equation number 4 and equation number 1. Okay. So this is your grad phi in orthogonal curvilinear coordinate system. Now, del operator in orthogonal curvilinear system also you can express it as, you just remove this scalar quantity. The del operator here in this case is given by this. You remember that the del operator in 3D Cartesian system, 3D Cartesian system was del operator was del upon del x I cap, del upon del y j cap, plus del upon del z k cap. So this was the 3D Cartesian del operator. But in the orthogonal curvilinear coordinate system, this is what we have as the del operator. All right. Now moving on to this divergence of a vector in orthogonal curvilinear coordinate system. So let us consider a certain vector A here. A certain vector A in orthogonal curvilinear system, you can express it like this. Here, A1 here is a function of, A1 here can be a function of coordinate variables are u1, u2, u3, and A2 can be written, A2 can be a function of u1, u2, u3, and A3 can be a function of u1, u2, u3. So this, I think you can understand from the analogy in the case of this, what is that? 3D Cartesian again. In the 3D Cartesian, you know that any vector can be written as a1 I cap plus a2, a2 j cap plus a3 k cap. So I, j, and k are the unit vectors in 3D Cartesian system. And in the 3D Cartesian system, the coordinate variables are x, y, and z. So in most general case, A is written as a function of x, y, and z. And similarly, A2 is also a function of x, y, and z. And similarly, A3 is also a function of x, y, and z. So similar to that, instead of I, j, and k, you now have unit vectors e1, e2, and e3, and a1, a2, a3, which are the functions of coordinate variables u1, u2, and u3. Now, when you take a divergence, that is del dot the vector A in this orthogonal curvilinear system, so you have to take it like this, divergence of this. So this divergence, del operator will operate on the first term, it will operate on the second term, and the third term like this. All right, just 1 minute. So now let us consider the gradient on the coordinate surface. We have defined this. I think you are familiar with the coordinate surface defined like u1 equal to c1, u2 equal to c2, and this. All right. So we can obtain the vector perpendicular to the surface as grad u1. Grad u1, you know that del operator in the case of this is this. So this is your del operator. This is your del operator. So just use the del operator here, grad u1. So if you do that, if you operate on this thing, del u1 upon del u1 is here 1, And here in the second term, del u1 upon del u2, del u1 upon del u2 will be 0. It's like u1 and u2 are the coordinate variables. So you know that when x, y, z are the coordinate variables in the case of this 3D Cartesian system. Differentiation of one coordinate variable with another coordinate variable is 0, right? Del z upon del x is 0. So similar to that, when you differentiate one of the coordinate variable with another coordinate variable in this orthogonal covariant coordinate system, it will be 0. And similarly, this term also, this differentiation also will result in 0. And this will result in 1. And what we have here is E1 upon H1, E1 cap upon tangential unit vectors upon H1, right? So similarly, if you take grad U2, this is what you're going to get. If you take grad U3, this is what you're going to get. Now consider the cross product between grad U2 and grad U3. So if you take the cross product like this, it will be E2 cross E3 divided by H2 into H3. So E2 cross E3 will be E1. Similar to this, right? J cross K is I cap, or I cross J is K cap. Cross product between two unit vectors results in the third unit vectors, which is perpendicular to the two unit vectors here. So similar to that, consider in place of I, J, K, you consider E1, E2, E3 now, right? So E2 cross E3 cap will result in E1, just like that. All right. So your E1 cap can be expressed as H2 into H3 into this. And similarly, following the same calculation, you can obtain your E2 as grad cross product between grad U3 and grad U1, and this, and similarly this, right? So now if you consider this divergence of A1 E1, divergence of A1 E1 here will be, you just put E1 as this. So it will be divergence of A1 into H2 H3, A1 into H2 H3, cross product between grad of U2 and grad of U3. Okay. Now the vector identity, I think I've given you as some exercise, this vector identity. So if you take a divergence between scalar quantity and vector quantity product, phi is here is a scalar, b is a vector. So divergence of scalar into vector, this will result in gradient of a scalar dot product with the vector plus phi, the scalar quantity, into divergence of the vector b. So here in the above expression here, you just consider this as your phi and this as your b vector. So it will be similar to divergence of phi into b vector, right? So this is grad phi dot b vector plus phi divergence of b vector. This is what we are going to get. Phi, you take it as this, b vector, you take it as this. So if you do that, this will result in gradient of phi. Phi is a1 h2 h3, b vector is this cross product between these two vectors, will result in another vector called, we just assume it as b vector here. So instead of phi, you just write a1 h2 h3 and divergence of this quantity. So again, there is a vector identity which you have to prove also for your classroom exercise. You revise this vector identity, that is divergence of a cross b. Divergence of a cross b will be written as b dot curl of a minus a dot curl of b. So if you follow that, you take a vector as grad u2, b vector as grad u3, then divergence of this will be this, right? So u2 and u3 are scalar quantities. So from vector identity, curl of gradient of any scalar quantity is always 0. Curl of gradient of any scalar quantity is always 0. This I think we have seen in the 3D Cartesian system. I don't know whether I have done the proof or not, but I think the mathematical steps are there in the notes provided to you, or otherwise you work it out, all these vector identities. So curl of gradient of phi is 0, and therefore curl of grad u2, curl of grad u3, they are 0. All right. So if they are 0, that means the second term over here will become 0. The second term is 0 here, and we only have the first term as this. Divergence of this is the equal to this. So grad U2, you remember that grad U2 is E2 cube upon H2. Grad U3 is E3 cube upon H3. So you just put the value of grad U2 and grad U3 here. Grad U2 you put it here, grad U3 you put it here. This is what you're going to get. And now if you continue here, this is your gradient del operator. Okay, del operator, you know that you can write it as E1 cap upon H1. See, del operator is E1 upon H1 del upon del U1 plus E2 upon H2 del upon del U2 plus E3 upon H3 del upon del U3. So if you follow the del operator that we discussed, so you just put here this A1, H2, H3 are scalars, so you have to put in all these terms. Okay, E2 cross E3 is E1, E2 cross E3 is E1, so E1 upon H2, H3. So here you take the dot product. Now there is a dot product here. E1 dot E1 is 1, E2 dot E1 is 0, E3 dot E1 is 0. So the second, this term and this term, if you take the product with this, it's 0. Only the first term will result in 1. E1 dot E1 is 1. So if we here, you are going to have 1 upon H1, H2, H3 multiplied with del A1 is del A1, H2, H3 upon del U1. Okay. So this is your divergence of A1, E1, the first term here. So the first term, you can deduce it like that. And you have the second term and the third term here when you take the divergence of a vector. So in the second term, divergence of A2, E2, similar to the first term calculation, if you follow that, it will result in 1 upon H1, H2, H3, and this differentiation. And divergence of A3, H3, the third term, it will result in this. So if you just put divergence of A, you remember, it will be divergence of A1, E1 plus divergence of A2, E2 cap plus divergence of A3, E3 cap. So this you have deduced it as this, and similar to this calculation here, you can follow this and you will get this, you will get this. So you can work it out. This calculation for divergence of E as this is shown here. Similar to this step, please prove this. Please prove this. Prove that this quantity is equal to this. Prove that this quantity is also equal to this. If you follow, if you do the calculation steps for this and get these results, I think you will understand and you will have more confidence about this thing. So after putting all these things, this is what you're going to get it as a divergence of a vector. Yeah, this is your divergence of a vector. I think I will stop here. I don't want to take a very long class at night. Probably day after tomorrow, we can schedule a class again, either in the evening or at night, whichever is convenient to you. We will see. We'll discuss about that. Okay, so I will stop here. So what I can suggest is that please revise the divergence cal and all that we discussed for 3D Cartesian system, and do this exercise, prove this. Okay, and also do this exercise, prove this and prove this. This proof you do it, this proof you do it, this proof also you do it. You can see my lecture notes I provided. So if the proof is not given in my lecture notes, you look for some books or you can work it out yourself. It's very simple. You prove these three identities. And if it is there in my lecture notes, you just study how these vector identities are obtained. Okay. And also here we have calculated for divergence of A1, E1 cap. and we arrive at this. But you have to do it yourself, that divergence you have to solve for you have to prove yourself that divergence of A to E2 cap is this. So if you work out all the mathematical steps for this divergence of A to E2 yourself and divergence of A to E2 yourself, then I think you will have more understanding on this particular topic. So whatever I'm doing here is just try to follow it and try to work it out and obtain this result. So I think that will help. So I suggest you do that. Okay. So if you have typed your attendance, I think we can end this session now, and hopefully we can arrange one more class.